Hello again, this is Galen Pickett, Cal State Long Beach. We're talking about Physics 151, and we're moving into Chapter 5. So I want to talk today about Chapter 5, Section 1, identifying the forces in the system. We're talking about how momentum changes in the system, the rate at which the momentum changes, and how that is dealt with the energy principle. So here are two situations that you'll deal with on your problem sets. Here I've got two objects. Here on the left I've got two objects that are being suspended by a rope. So I've got three sections of rope and two masses. On the left I've got a person who is standing on a frictionless surface, but there is this ramp at an angle theta. There's a wheeled cart, so there's no friction there. If the person let go of their rope, that box would roll downwards. In each of these questions, say I can ask, in order to find out how the objects are going to move and what the forces are, I need to divide up the universe into the system and the surroundings. So let's say that the system for the box problem, I'll just even draw a boundary here. Here is the boundary, the system boundary for the box. So the box is the system. And everything else is in the surroundings. So I've got me, I'm the person here at the top, I've got the rope, I've got the surface that the system is resting on, that is the ramp. And we've also got the earth in these surroundings, that's providing the gravity force that the person at the top there, me, has got to support with this rope. So if the system is just this box, we're going to model that for the purposes of the momentum principle with just a dot. So there is the box. Everything that's in the surroundings has got the right to put some interaction on the system, and those interactions are forces. So we've got to figure out what are all the forces that are actually touching the system, that are actually influencing the momentum of the system. So first, let's look at the easiest one. You can never get away from the Earth. There is always going to be a weight force from the Earth. So there it is. It points downward. That's going to be, if I knew what the mass of this box was, m times g. The ramp, if the ramp were not there, then the box would be hanging straight downward. So there is a force from the ramp. I'll give that the name normal force, n. And it is tilted at an angle theta from the vertical because the ramp is tilted at an angle theta from the horizontal. The normal force is perpendicular to the surface. The rope is the actual part of the rope that is crossing the system boundary, and that points up the field. So I'll call that the tension. That's the rope force. And that is tilted at an angle theta. It's parallel to this surface. The only thing we've got to decide is, should my force be sitting on this, be sitting on here? Now, and the answer to that is no. I am touching this piece of rope. That piece of rope is not touching the box. So if I was going to make a system for the rope would be affected by a force from me, and I pull the rope upwards, but it would also be affected by a force downwards, a force from the box. And that would tell me how the rope moves. You only deal with the forces that are actually crossing the system boundary and are touching your system. So I do not put me. I am in the surroundings, but I'm a part of the surroundings that doesn't affect the system. Now, how did we deal with the momentum principle here? If I'm holding the box static, I need that the momentum, the rate at which the momentum of the box changes, that's what the momentum principle tells me, is equal to the F net from the surroundings. That's always what the momentum principle says. And here is the net force diagram. So I've got all those forces. I can resolve them into components, but for this purpose I would have normal force plus the weight plus the tension. And because the box is standing still, the rate at which the momentum changes is 0. That's a static problem, and there is what the momentum principle says for the person holding up the box. For these hanging masses, let's take this mass to be our system. So let me call this one A and this one B. So I want to know what are all the forces that are affecting B. I've got the system is equal to B. So I'm going to give these ropes names. This is rope number 1, rope number 2, and rope number 3. So the surroundings is everything else in the universe. So I've got the Earth, which is pressing down on, is pulling the mass B downwards. That's always going to be there. I've got ropes 1, rope 2, and rope 3. Those are all in the surroundings. And they've all got the possibility to be on the net force diagram. So now let's make the net force diagram for B. So there is the mass. It's got a mass M, and I'll just put off to the side here that we're talking about B for the system. Now here's the system boundary. I sketched it in right there. I'll highlight it. There's the system boundary. The only things that are crossing the system boundary, there is a force from rope 3. There is a force from rope 2. But there is no force from rope 1. Rope 1 touches mass A. And then mass A touches rope 2. And then rope 2 touches mass B. So we do not need to know, rope 1 is not something that goes on the net force diagram for mass B. What the momentum principle will say is dp dt for our system B, well, I can see that it's static, it's stationary, it's equal to 0. That's what the momentum principle says, and it's equal to the net forces here. I've got tension 2, that is the force from the rope pulling it upwards. I've got tension 3, that's the rope that is pulling it downwards, and then I've got its weight. I'll write that as W sub B. And that is the statement of the net forces for the right system.